Yeah, hello. Good morning to all of you. I hope you can hear my voice. If so, please, anyone do respond.
Yes, sir.
Okay, good. I got a response. So could you also see the screen? You should be able to see the presentation with the title called Crystalline Material, something like that.
Crystalline materials. Yes, sir.
Yeah, this screen should be visible. All right, so if everything is fine, we can begin. I hope everybody, not everybody, today we have 28 students who have joined this class. I hope everybody will join soon. So now let us begin with the lecture for today, which is on crystalline materials. And crystalline materials, as yesterday we were talking about broader classification of various branches of physics, and there we saw how do we come across various branches of physics in terms of the different length scales which we have to encounter in uh, uh, various branches of physics. For example, in nuclear physics, you deal with the length scales of the order of 10 to minus 15 meter or so. So in condensed matter physics, we deal with the length scales of the order of say from some angstrom to a few nanometers or 200 nanometers. Now, as I had shared that okay, we have to cover certain course contents, and okay, so the Ish is joining now. We have to cover certain course content, and the first unit is on crystalline material. So these crystalline materials are the simplest of all the materials in a sense that they have a very well defined arrangement of the atoms. And if we see uh, in that yesterday's slide also we have seen this that okay, matter usually or conventionally is classified into three main states, which are liquid, solid, and gas. And of course, there are other states as well, like plasma, Bose-Einstein condensate. All those is not the topic as of now. So this is just very what you would say preliminary way of classifying states of matter, or broadly how we can classify. And among solids, so during most of our course, we shall be concerned with the solid state, and in solid state too, we shall be concerned with the crystalline solids. So, what are crystalline solids? If you can see this slide, then you will realize from here that okay, there are three types of solids which have been demonstrated here. This is just a schematic representation. So one type of solids are crystalline solids, where you would see these circles are representing atoms in the solid. So you will see that in crystalline solids there is a very systematic uh, periodic arrangement of the atoms. And on the other hand, when you go to the extreme right, you will see the amorphous solids where atoms are there, but these are not following any specific pattern. So these are two extremes in the solids, crystalline solids and amorphous solids. And somewhere in between comes the polycrystalline solids. So what are polycrystalline solids? Are like crystalline solids themselves, but those crystalline solids are not extending to a very large length. So in an ideal crystal, the periodicity retains itself to a very large lengths. And what do we mean by large length? Ideally, a crystal should be something like which extends all the way to infinity, isn't it? So it should satisfy the periodicity. It should satisfy the periodicity condition, and according to that, any function should repeat itself after certain period of time. So in crystalline solids, in ideal case, they should have atomic periodicity up to infinity. And what would that mean? A crystal, if it really exists, a real crystal in nature, should be capable of filling the whole universe, which practically is not true. So how do we define a crystalline solid? In real life, actually, the crystalline solids are those for which the length over which the atoms are periodically distributed is very large in comparison to the interatomic separation. For example, let us take a case of, say, sodium chloride crystal, the common salt at our homes. And typical lattice constant in the crystals for sodium chloride, I think it is somewhat like 5 angstrom or something like that. So 5 angstrom. I hope you do sit with the notebook in your hand. If not, you can just take a notebook or some page and then try to do some calculations, which I may recommend during the class. So if you talk of, say, sodium chloride, so for this, if today you don't have a notebook, don't worry. You can just keep the things in your mind and do the calculation later after this lecture. So if you take the case of, say, sodium chloride, assume its lattice constant. You can search for the exact value on Google, but okay, let me give you a rough idea. Suppose that is 5 angstrom. Then if you take sodium chloride crystal and take its lattice constant, so this is a face center cubic. So it has a, say, lattice constant of, say, 5 angstrom. In that case, let us consider that, okay, we have a sodium crystal of something like, say, 1 millimeter by 1 millimeter by 1 millimeter. You can assume how small is 1 millimeter. I hope you have a fairly good idea of lengths. So 1 millimeter is very small, right? Typical grain of a salt. Then if you try to calculate how many unit cells of sodium chloride would be required to make such 1 millimeter by 1 millimeter by 1 millimeter crystal of sodium chloride, that number comes out to be really very large. So I leave it to you, but yes, this number will be something very, very large. So what you have to do is, you have to take 1 millimeter, means 10 raised to the power minus 3 meters, which has to be divided with 5 angstrom, right? So something like 10 raised to minus 3 being divided with the number 10 raised to power minus 10. So it would be something like 10 raised to power 7. So you would something rough orders of magnitude. So you will soon realize that the number of unit cells which are repeating to make even a very small crystal of size, say, 1 millimeter by 1 millimeter by 1 millimeter would be something like 10 raised to power 7, which is a very large number. So under such situations, we can say, okay, this crystal is fairly good to be called as a single crystal. So that's what we call. That's why we call the certain crystals as single crystals. Means that length is very large. But in practical situation, it may not happen. And whenever we grow crystals, we may not get such large size single crystals. And typically single crystals can be even larger. 1 millimeter is very small size, which I'm referring to. And when you grow single crystals in lab, you can get single crystals of the order of few centimeters, and even people have tried to work with the single crystals of few tens of centimeters. Even maybe you can try to Google that, crystals of size of some meter maybe, but those are rare. I mean, those are very hard to grow. So practically, when you try to grow crystalline materials, usually what you get is polycrystalline material. Means whenever you are growing a material, the periodicity of atoms is not infinitely repeated, but it is repeated only up to small lengths. So such crystals, and then what may happen is that after certain distance, the periodicity is broken. So those kind of materials are termed as polycrystalline. Now you would say, okay, periodicity is being broken, then why don't we call them amorphous materials, isn't it? So they are not amorphous because the periodicity is not that short range. Say in case of, say, single crystal, if the number of unit cells which are repeating, if they are of the order of something like 10 to the 7, Then in polycrystallines, there may be something like 10 to the power 3 or 10 to the power 4. Then still we will say that, okay, at least 10 to the power 3 means 1000 unit cells are repeating without any defect, and then some dislocations or some defects, some orientational defects, uh, uh, some dislocations are coming. So that is okay. I mean, 10 raised to the power 4 is a fairly good number of unit cells. So that is why we can term them as the polycrystalline material. I mean, these are still crystalline. So if you do an X-ray diffraction measurement on such even polycrystalline material, you would see very nice peaks as per the Bragg's law in those crystals as well. So that's the main difference, right? So now after this slide, you should be in a position to differentiate between single crystals, polycrystalline materials, and amorphous. So in amorphous materials, you don't even have that short range periodicity. Short range, I mean, there is no periodicity. They may have even, I mean, amorphous material may have a local periodicity. Local periodicity may be something like, okay, I won't say periodicity, but they may have a local order. And a local order means that, uh, for example, we take a molecule of methane. So the atoms of hydrogen are arranged in a specific manner around carbon atom. So that we may call as local order. So methane molecules will all be identical. But when you try to say consider of many molecules of methane taken together, so they may not have same they may not have a well-defined periodicity, that okay, one molecule is repeating after other after certain specific distance. Even if they are repeating, you may find out that okay, the orientation of all the molecules may not be exactly the same way. So for even molecular crystals, there do exist molecular crystals. For example, even oxygen, O2 do crystallize. Many gases do crystallize at a very low temperature and very high pressure. But there, the basic qualifying definition for something to be called a crystal is that there must be periodicity of certain units, and those units should also be placed in a exactly same manner. Means their orientation should be exactly same, and they must be repeating after a fixed distance. So that's the basic difference. So if you are asked to define what is a crystalline material, so a crystalline material is a material which repeat itself, and over a long, I mean, a crystalline material is a material in which the constituent units like atoms or molecules do repeat over a very large lengths, and the repetition is regular. There is no irregularities in between. So one defining factor is they should have long range periodicity. That's what very important thing, long range periodicity. So even in polycrystalline material, yes, they do have a long range periodicity, and long range means in comparison to the interatomic separation or the lattice constant, the periodicity goes over a large number. I mean, something like of the order of 10 to the at least to say 10 to the 3, 10 to the 4. So that is the way to define crystalline material. So long range order is something very important. Now, when we are discussing with the when we are discussing the what you call these periodic materials or crystalline materials, we come across the concept of symmetry, because whenever we are dealing with repetition of something, then that will be associated with certain symmetry, and repetition in itself may be termed as symmetry, right? For example, if you take say one dimensional arrangement of points, and all those points are repeating after certain specific distance, then in that case we may say that those points have a translational symmetry, right? Means the if you say move along the length, then you will find out that after certain fixed number of steps you will be finding exactly the same environment, and that is what is called the symmetry. And As such, there are two types of repetitions which are possible. One is translation, as I already told that, okay, if you move along a particular direction, you will find that, okay, certain things are repeating after a specific uh, separation. So that is translational repetition, and second is rotational repetition. For example, you may have some atom at say 0 degree. If you take one line, then you may have an atom at say 0 degree, then maybe somewhere at say 30 degree, maybe 60 degree. For example, in case of hexagonal lattice, you have a rotational repetition as well. After every 60 degree, I think, yeah, the atomic units are repeated. So that is rotational periodicity. So you have two types of periodicity. Now, okay, first of all, let us try to ask question of what is the meaning of rotational symmetry. So what do we mean by rotational symmetry? Let me try to demonstrate that with the help of this simple figure. So this is a square, right? Now let us assume that we pass one axis perpendicular to this square passing through its center. So I hope you know what is the meaning of center of a square. So if we take a perpendicular axis and pass this square to pass a axis perpendicular to the center of this square. Now let me tell you that, okay, let us do a rotation by an angle of 90 degree. So can you really be in a position to tell me whether, okay, from this slide, when I went to this slide, did I do any rotation by 90 degree? Will you be in a position to tell me this? I'm sure no, because it's not possible to uh, by any means to see that whether this has been rotated by 90 degree or not, because the square will look exactly same after the repetition or after the rotation of 90 degree, and that is what we call the symmetry. So what does so object, that is why we can say that square is symmetric with respect to 90 degree rotation. The square is symmetric with respect to 90 degree rotation. So what does this mean? Oh, if you do any other rotation, I mean, other than 90 degree, if I rotate this square by say something like 30 degree, yes, we will be in a position to tell, yes, this has been rotated, because in that case, a corner which is somewhere at say extreme right will be tilted a little bit by an angle, say 30 degree or so. So that is not symmetry operation. But yes, rotation by 90 degree is a symmetry operation, because then if we won't be in a position to tell whether the square has been repeated or not. So that's what is the meaning of symmetry. I mean, doing nothing, or at least doing something which is not possible to be detected. We can't uh, detect that change, or we won't be in a position to tell whether that has been done or not, that operation has been done or not. Those operations are called symmetry operation. So I hope, I mean, doing nothing or at least doing something so that it is not possible to define whether something has been done or not. That is called a symmetry operation. Now, okay, you can now try to look at the same figure and try to spot or try to find out that what all other kinds of symmetry operations this square do have. So, of course, it has one 90 degree rotational symmetry. Then, of course, 180 degree will also be there. So that kind of symmetry operation, I hope you have done it in your BSc classes, right? That we can say that a square has a four-fold axis of symmetry. What do we mean by four-fold rotational axis of symmetry? So we have to take a, if any figure uh, rotated by an angle 2 pi by n, where n being an integer, and then that 2 pi by n rotation is a symmetry operation. If that 2 pi by n is a symmetry operation, then we say that the diagram or the figure or the object has n-fold rotational symmetry axis. So in case of square, what will be that? N In this case, if we take 2 pi, which is 360 by 4, and this gives you 90 degree, right? So in this case, a square has a 90-degree rotational symmetry. So we will say that there exists a four-fold rotational axis of symmetry for a square. Similarly, you can try to see it for other figures as well. For example, if you take a hexagon, what should be the n value? I mean, how many fold axis of symmetry should exist there? I leave it as an exercise to you. Similarly, if you take a rectangle, then what should be the n value? I mean, what fold axis of symmetry? Fine. It's not only rotation, which is a symmetry operation for a square, but yes, in a square, we do also have a mirror plane, right? So what do we mean by having a mirror plane? So it has a mirror plane, means if I place a mirror along this vertical line in a square, then we will see that the left half of the square is exactly the mirror image of right half of the this square, and that is what we call the reflection symmetry, or that is what we call the existence of mirror plane of symmetry. So that kind of symmetry operation is represented with the help of a number called m. M stands for a mirror plane. Now I will give a pause to make you realize that what other kind of mirror planes do exist for a square. Try to imagine what other kinds of mirror plane do exist for a mirror. So one is this one, isn't it? So these two mirror planes are identical, so they are written with same symbol, say m. And is there any other possibility of mirror planes for a square? Okay, so yes, of course, there will be a mirror plane along the diagonal. So you would see that for a square, this half is the mirror image of this half. So there is another mirror plane as well. So that is how we represent the symmetry operations for a square with the symbol 4mm. So 4 means it has a four-fold axis of symmetry. M means it has a mirror plane, and M is coming 2 times. What does it mean is that it has 2 different types of mirror planes which exist there as a symmetry operation for, or which are there as a part of reflection symmetry in a square. One set of planes are bisecting the edges, other set of planes are passing through the diagonals. So that is how we can represent the symmetry operations for a square. I hope that you are able to get this idea. Similarly, this example of hexagon, so these are the symmetry operations which exists for a hexagon. So it has a 6-fold axis of symmetry. 6-fold means if you try to imagine by what rotation, if you rotate a hexagon, you should be in a position, you should not be in a position to tell whether the rotation has taken place or not. So it should be 60 degree, right? If you take a hexagon and rotate it by 60 degree, then you can't tell whether rotation has happened or not. Means that is a symmetry operation. So in this case, what should be n fold axis of symmetry? So 2 pi by n should give you 60 degree. And what should n be? 6. So in that case, it has a 6-fold axis of symmetry, 6-fold rotational axis of symmetry. Similarly, it also has 2 sets of planes, mirror planes. So one are, of course, bisecting the sides of the hexagon, and then others are passing the or connecting these points joining the sides of the hexagon. So that is how we can represent the symmetry operations for a hexagon. So these numbers are used in describing the symmetry operations. So when we will discuss the space groups or point groups, there these numbers will appear. So this is sort of representing a point group, means what is the local symmetry of a particular object. So 6 mm is the symmetry for this. So you can try this yourself. I again leave it to you that you try to see what should be the symmetry elements for a this is a parallelogram. So you try to do it yourself. Now let us talk about, so that was what kind of rotational or reflection symmetries may exist for different objects. Now let us talk about translational symmetry. So translation can also be seen in similar way as we have seen for rotation. Let us talk of the case of a one-dimensional array of points. As of now, I'm not talking to you directly in regard to the crystals. Means I'm not mentioning as such what atoms are there in the crystal, what is lattice, what is basis. No, I am just talking of periodicity. We are just trying to understand how periodic structures can be described. Then we will take these concepts of periodicity and then apply these to the crystal structures. So as of now, it is just uh, to understand what is symmetry and how does periodicity lead to different kinds of symmetries. So okay, if we take this one-dimensional array of points, then that has of course translational symmetry. What is the meaning of translational symmetry? That I mean, translational symmetry means if I am at one of the points on these one-dimensional array of points, and if I move from one point to the another point, then on both these points, I would be noticing exactly the same environment. Means I won't be in a position to tell, okay, if I have gone from one point to another. I mean, okay, I can, if we take ourselves as observer and then say, okay, I have moved from one point to another, then we may say, okay, I have moved, so I can tell, yes, I have gone from one point to another. No, that's not the way. But okay, I am at one point and somebody took me to some other point, or I did a translation without uh, actually being told that, okay, I have done a translation. And then uh, I am asked to check as if I have gone through a translation or not. Then, if the translation is from one point to another point, please note my words carefully. If the translation is from one point to other point, then we won't be in a position to tell whether we have undergone a translation or not, because all these points have exactly the same environment. You sit on any of these points, you will see what is the environment. You have a one point, so suppose this interpoint separation is A. Then if you are on any of the point, what is the environment of this point? To the left side, there is a point at a distance A, and same is the case to the right hand side. There is another point to a distance A, and then similarly you have a point to a distance 2A on the left hand side and another point on a distance 2A to the right hand side, and this repetition continues indefinitely. So that is why on whatever point I am, I would be seeing exactly the same environment. So we can't tell whether there has happened any translation or not. But yes, if somebody takes you from one point and leaves you at somewhere in between, midpoint of the 2 points in this repetition, then yes, you can tell that there has been a translation. Because when you move from one point to the midpoint, what happens? I don't know if you can follow the cursor on my screen. If so, that will be helpful. So, okay, I mean, suppose we go from one point and stop at the midpoint between the 2 points. Now environment has changed. Now, to your left-hand side, you have a point which is at, say, a by 2 from your location, and to right-hand side also you have a point at a by 2, which is in contrast to the earlier case when we had a point to the left hand side at a distance of a, and another point to the right hand side at a distance of a. But here, so I mean, all those translational operations, after doing which we can't tell whether translation has happened or not, are called symmetry translational operation. So even in periodic structures, every translation is not a symmetry operation. Only those translations are symmetry operations which follow certain specific rules. So that is something which you should highlight, or you should notice carefully. So translations that are restricted only to certain values to get symmetry. That is what is the main thing here. I hope you got the idea. Let me pause for a moment and ask you to ask any questions if there are any doubts. You can ask by unmuting your mic, or you can even put me your comments in the chat box. So right now I am watching your chat box, or even I may be listening to your voice. Any questions till now? Yes, any response from anyone in the audience? Shreya is saying this is clear. Okay, it may be clear for Shreya. What about others? Okay, fine. Okay, who is Dharmendra? Someone leaves a meeting, then joins. I don't know why this keep on happening. Maybe you have some network issues. Okay, fine. If it is clear to all of you, well, let us move to the next thing. I would like to know why people keep on leaving, joining. Maybe network issue. Fine. Let's move to the next thing. So that's about translational symmetry. Similarly, we may have that was simplest case of one-dimensional repetition. You may have two-dimensional repetition, and there are a lot of possibilities there as well. So let us consider this case of two-dimensional translations. So here, what is the meaning of two-dimensional translation? We have, you can see this figure. There is a repetition of something like these parallelograms, right? These are being repeated, and let us assume they are repeating infinitely. So how we can represent these repetitions? I mean, instead of representing the whole structure, we may prefer to take a point corresponding to corresponding to each structure. I mean, instead of representing the whole parallelogram, let me take a dot for each parallelogram. So you pay attention to this. Okay, this one in the center, right? So for each parallelogram, you're taking a point. So if I take a point for each parallelogram, how can I repeat the whole structure, or how can I represent the whole structure, whole periodic structure? I can represent the whole periodic structure with the help of this set of points. So that is where the idea of lattice comes in context of crystal systems. So what is a lattice actually? Instead of representing the whole crystal, we try to spot first what is the repeating unit in a crystal, and then corresponding to each repeating unit in a crystal, we assign a point, and then we repeat all those points in a crystal, and we call that repeating points, or the set of repeating points, as a lattice. So that is how we represent a crystal with the help of two components. One is lattice, which is periodic repetition of the points, and another one is basis. I will be talking about basis. So in this case, we can say, okay, the array of points on right hand side is representing the lattice for this periodic structure. And what is the basis? Basis constitutes the rectangle. Have any structure in between. I mean, okay, within every rectangle, we may draw a pattern, and then all those rectangles are identical and repeating. Or within a rectangle, we may have some set of dots, or some set of cross, or whatever kind of structures. Every rectangle may be having, say, two flowers, one of rose, another one of some other flower. So so that kind of pattern, which is to be associated with each lattice point, we may call that as a basis. Fine. So what is the advantage? Okay, now you may ask question, okay, if you have a periodic structure, what is the advantage of using these points? Why we shift from periodic repetition of structures to periodic repetition of just points? The advantage is that these points are convenient to deal mathematically. We will be realizing this soon. So the mathematical description of these points is relatively simple. So in case we have a full structure, you have to describe, okay, if how is a rectangle itself. So you may have to describe, okay, at one corner, for example, let us assume at one corner of this rectangle there is a dot, and maybe suppose at other corner there is a cross, at other corner there is a dash, other corner there may be a slash, in the center there may be something like a rose flower, and so on. So that is the internal structure of each repeating unit. So rather than representing the whole structure as such, we say, okay, let us first try to identify what is the periodicity. I mean, how the things are repeating. So that repetition has its own character. In this case, the repetition is having a specific symmetry. So these set of points have a specific symmetry, and they satisfy a specific symmetry operation. And then there may be some other kind of repetition which may have a different symmetry, right? So to locate the uh, different symmetry operations in a crystal, we may have to take help of these points. So that is what we call the lattice, as I already defined for you. Now let us come to the defining condition for a lattice. To what all we can call a lattice. It's not that any arrangement of points is called lattice, but yes, the arrangement of points which satisfy certain conditions is called lattice. So what is the condition is that it should be infinite arrangement of points, and it should be perfectly periodic. The periodicity should be perfect. So infinite, perfectly periodic arrangement of points in a space is called a lattice. So fine. So this is a lattice. So what all is not a lattice? So let us take this. This is a perfect lattice. If I move to this is not a lattice. So what has happened? The exactly same previous structure, but one of the points in the lattice is displaced from its location where it should be as per the requirements of being a lattice. So this is not a lattice. So even if one single point fail to satisfy that condition of periodicity, we are no more talking of a lattice, or that whole arrangement is no more a lattice. Even a single point, if it doesn't fit on the proper location, that is not a lattice. So this is not a lattice. Fine. Similarly, this is also not a lattice. Why? Because so here you may say, okay, this is a perfectly periodic array. Everything is sitting at its respective place. Perfect. But it is not a lattice. Why? Can you think over this? Why this is not a lattice? Because everything is still periodic. Everything is sitting perfectly. Now, answer to this is not that it is not infinite. So we can't, of course, show infinite things on screen. But okay, I say that these arrows are representing the infinite repetition. So this is still not a lattice. Why so? Because, yes, any response? Why this is still not a lattice? Yes. Any response, right or wrong, whatever, oral or typo, you can put it in chat box or speak out. Why it is not a lattice? I can't hear anyone. I can't see any response because it's not perfectly symmetric. Very good, Ankush. I saw some response. Any other response? It is not perfectly symmetric. Fine. What else? Not an ordered array of points. Harish. Okay. Anyone else? Yes, I want. Okay, any two responses, please? Any two students? What do you think? Why it is not a lattice? It contains two different types of points. Okay. One last response at least. One last. Himanshu responded, very good. Harish responded. Ankush responded. Dipali, very good. Not a regular array. No, it is a regular array, fine. But the main thing is that a lattice is a periodic arrangement of points only. In this diagram, these are not just points, but this is a sum structure. You can see there is one dot associated which is smaller, and there is a bigger dot or a green and some white dot, right? So that is why it is not a lattice. It is some periodic structure, but not a lattice. So for something to be called a lattice, it must be a periodic arrangement of points. And what do we mean by points? They don't have any dimension. So those are just zero-dimensional dots. So in this case, it is a periodic structure. Perfectly fine. It is a periodic structure, but it is not a lattice. So that's what is the whole idea. I mean, in a crystal also, that is a periodic structure. And then out of that periodic structure, the whole information of that periodic structure, we try to break that into two components. One is lattice, which is just periodic arrangement of points. Another one is the basis, which tells us how does each point contain a local structure, or what is the local structure associated with the each point. Got it? Fine. Now that's the thing. Means this has some kind of structure associated with it. Fine. So now what we have done till now is that, okay, we had a periodic structure. Now that's something which we should highlight and notice with care. We had a periodic structure, like a crystal structure or a structure of two-dimensional, say, rectangles which are repeating. Fine. So from a structure, we moved to abstract arrangement of points. That is what we call the lattice. Fine. Now we have, for a periodic structure, a periodic lattice, which is just trying to represent the whole structure in the form of abstract points. Now, it doesn't make sense to represent the whole infinite set of points because they are just repeating and following certain rule. So the idea is that why to actually represent the whole infinite thing when we have a better option for that, and that better option is that, okay, let us try to find out the smallest repeating unit. And the first thing is the smallest repeating unit, and second thing is that how is that repeating unit uh, repeating itself, means the rule according to which the smallest unit is repeating, and what is that smallest unit. So that is how we define a unit cell in a whole lattice. So unit cell is actually the component of a lattice. I mean, it is the smallest repeating unit which repeats the whole lattice, which has a capability of getting the whole lattice. So this, for example, on the left hand side is a periodic arrangement of the lattice points. Instead of representing the whole infinite array of points, we prefer to talk of a unit cell, which is the smallest repeating unit. It is not necessarily the smallest repeating unit. It is the repeating unit which repeats itself to form the whole infinite array of the points. Now you will say, okay, if it is not smallest unit, then why we even talk of the unit cell? So I mean, the unit cells have their own convenience. So sometimes we may be comfortable with the smallest unit, sometimes we may be comfortable with unit which is not smallest but has better symmetry. For example, in case of cubic crystals, we have something called face-centered cubic arrangement, FCC crystals, or FCC lattice actually. So FCC is a lattice, not a crystal usually. So we call it wrong way. So if you have a FCC arrangement, then in that FCC arrangement, that FCC is not a primitive cell. We will be coming to that. Means it is not a smallest unit cell, but it is still it is used as the unit cell to represent that kind of structure. Why? Because the cubic cell has more symmetry elements, and if we will see the corresponding primitive cell or the smallest cell corresponding to that FCC lattice, that is not a cube. So I'll be demonstrating that one in the coming classes or maybe coming slides. So fine, anyway, I mean, we have something called a unit cell, and then the question is, okay, how we can represent a unit cell? So unit cell in a case of two-dimensional lattice. Now I hope you know lattice, you know a unit cell. So in two-dimensional lattice, a unit cell is represented by two lengths and an angle between them, isn't it? We have to define two lengths, say one along say A direction, other along B direction, or one along X direction, other along Y direction, and the angle between them. So in this case, you have two different lengths. You may call them A or B, and then you also have to define the angle between them. That's the one way of representing unit cell. Other may be that, okay, we define two vectors. So when we are defining two vectors, we automatically are talking of the angle between them, because yes, once you know the vectors, you can always find the angle between them. So that's the information. I mean, we have to supply equal amount of information. So you may supply it one way or the other way. So in first way, we can define two lengths and the angle between them. So length A and length B, and then angle between them. Or alternatively, we can define two vectors. So that's one and the same thing. So in case of two-dimensional arrangement of points or two-dimensional lattice, we can define unit cell with the help of basis vectors. So let us choose the other or the second method of taking vectors. So we define, okay, this A vector and B vector as say the basis vectors. We call them basis vectors. Why basis vectors? Because these are the vectors which, when repeats in the whole two-dimensional space, they will be capable of producing the whole two-dimensional array of points. So that is why they are called the basis vectors. So in this figure, for example, if we say if this is say A direction, then there is one point sitting here. If you repeat along A direction, you will be getting all those points, all repeating after say length A and along direction A. Similarly along B, and then how to get this one? Say the other corner of the parallelogram. Let us say A is not B, so we may call it as a parallelogram. We can get that by a translation of one unit along A direction and then a translation of one unit along B direction. Fine. Now comes the part of that translational symmetry. So what is translational symmetry? We can say, or we can define here according to this equation. So any translation which is followed according to this law. So I mean something like t is equal to small t. These are integers. So t is an integer. Or you can say n1a, n2b, something like this. And this is not necessarily same. I mean ta and tb. It's not necessarily ta and tb. It may be t1a, t2b. I mean these two integers may be different. n1a, n2b. So all those translational operation. Translation, what do we mean by translation operation? Means we are moving as per the translation defined by this equation. Means this is just defining the path along which you have to move. Or I mean, it tells you, it doesn't tell about the path as such, but it tells you the position of initial and final point, which are part of the translation. So all those translations which are according to this rule are the symmetry operations. As far as this t1 and t2 are integers. So let us take this example, say of this translation, which is being shown by an arrow, longer arrow here. So what is this translation? You can try to say, we can try to see this as, okay, along B direction, we have 1, 2, and 3 unit. Along B direction, it is 3 unit. And along A direction, it is 1, 2 unit. So it is like, okay, 2A plus 3B. You can take it other way also. I mean, let us first go along 2 unit along A direction, then come 3 unit along B direction. That is one and the same translation. And this translation is a symmetry operation. How? So since this is a periodic array of points, means it is repeating infinitely. So as long as you are sitting on any of the lattice points, not only this translation, but you sit on any of these lattice points, you will see exactly the same environment. Means if you sit on any of the points and then somebody asks you, okay, the whole background of points have been moved with you asked to close your eyes, and then somebody moved the whole background, and then you after you open your eyes you realized, okay, you are again on the same on a lattice point. Okay, you were earlier on some lattice point, and then after that the whole lattice was translated, you realize that, okay, you are again on some lattice point. So shall you be in a position to tell whether the whole lattice have been moved or not? No, because earlier you were at a lattice point. How will you check? Okay, you will see all the surrounding and then you will realize, okay, everything is same. Then you are asked to close your eyes. Maybe somebody did the translation as per this translation vector, which is given here by this equation. And then when you were asked to open your eye, suppose you opened your eye and you are again on some lattice point. Now this lattice point may be some other lattice point, but since you are not in a position to distinguish between the points, because those are points, zero dimensional dots, so means you can't distinguish. Other way to check is to see your surrounding. So again you will see that, oh, everything is same around you. So means you won't be in a position to tell whether such kind of translation happened or not. So that kind of translation operations are called the symmetry translation operations. I mean, those are translational symmetry operations. On the other hand, if the translation is done such that this say t1a t2b or n1a n2b, whatever, one of them suppose is not an integer, so in that case you may be doing a translation say along by say 2 unit, but along b suppose it is 2.5 unit. So that translation operation is not symmetry operation, because in that case the surrounding will change and you will no longer be on a lattice point. So that is not a symmetry operation. So I hope till now you are in a position to define what is a translational symmetry operation or even a rotational symmetry operation, what all or how mathematically we can describe a translational symmetry operation for a periodic array of two-dimensional points. Similarly, in 3 dimension, we will be having 3 basis vectors, just like in 2D we had 2 vectors. Here we will be having 3 basis vectors, A, B, and C, and then the rules are exactly the same, and that is how we define a 3-dimensional lattice. Fine. So, and the how can we define the translation operation for 3-dimensional case? So it can be defined with the T translation vector is equal to say n1a plus n2b plus n3c. Let's not stick to these notations given in these slides. They're a little confusing. I mean, you have to take n1a, n2b, n3c. A, B, C are the basis vectors. n1, n2, n3 are some integers. So as far as n1, n2, n3 are integers, the translational operation will be the symmetry operation. If any one of n1, n2, or n3 is not integer, that operation won't be a symmetry operation. So I hope that is clear. Now, depending upon how these or what are the lengths of these vectors in 3D case, we I mean, to define 3-dimensional periodic structures, we have different options. So these options are maybe called as say lattice parameters. So as in case of 2D, we had 2 options, either to define 2 lengths and 1 angle, or to define 2 vectors. Similarly, in 3D case, you have, so these are the lattice parameters. So means you may define 3 lengths and 3 vectors, sorry, 3 lengths and 3 angles, or you may define 3 vectors. That's equally well. So those may be called as lattice parameters. So in 3D case, you have 6 lattice parameters: A, B, C, alpha, beta, gamma, or In same way, you may call, you have um, three vectors. I mean, you may have first vector which is having three components, other vector having three components, third vector having three components, and so on. So now, depending upon what are the values of these lattice parameters, you define different crystal systems. Say you have done it in your undergraduate, so I won't be doing this in details. That okay, what are the crystal systems? So you have 7 different crystal systems, depending upon what kind of lattice parameters are there for the lattice. Again, lattice parameters. Pay attention to these two keywords. So these are the parameters of the lattice, means they are characterizing the lattice. Till we are not talking of crystal structure, we are just talking of lattice only. So lattice parameters do describe the lattice. So similarly, in say you have triclinic lattice, you have monoclinic lattice, you have orthorhombic lattice, trigonal lattice, sorry, tetragonal lattice, cubic lattice, hexagonal lattice. In cubic lattice as well, I mean, what kind of repetition of lattice points is there? So these are 7 crystal systems. Now, each of these crystal systems may have different types of centering consistent with the symmetry. I mean, for each of those crystal systems, the lattice points may have different types of repetition. And there are total 14 combinations as such. I mean, it's not, it's within total 7 lattices, there are various types of um, uh, symmetry of the points in the, you can say, unit cell. So in triclinic primitive means you have only the lattice points sitting on the corners of the unit cell, something like that. So means effectively you have only one lattice point in the unit cell, and that is what we call the primitive cell. Similarly, you may have a monoclinic where P is primitive, I stands for body centered. So we will be coming to that maybe. Yeah, we will be coming to that in our coming classes. In orthorhombic, you have 3 options: P for primitive, I for body centered, F for face centered. Repetition of lattice points means body centered means you have lattice points sitting on all the corners of the unit cell as well as in the center of the unit cell. Similarly, face centered means you have lattice points on the corners of the unit cell and centers of the faces of the unit cell as well. You may have in orthorhombic A centered means only along one particular faces you have lattice points sitting on the centers of those faces, not on others. So similarly, you have tetragonal, for which only 2 possibilities are there: primitive and body centered. In cubic, you have primitive, body centered, and face centered. Cubic, you have done them most of the times. So simple cubic, body centered cubic, face centered cubic. In hexagonal, only primitive option is there. In trigonal, primitive and rhombohedral centered is there. So if you count all of them, so this is 1 2 3 4 5 6 7 8 9 10 11 12, then 1 for hexagonal 13 and 14. There are total 14 Brevis lattices. That's what we call. And now you may ask that, okay, why in case of say triclinic we don't have say face centered, or in cubic we have body centered, primitive and face centered, but why not in tetragonal we have a face centered? So answer to all this is limited, the detailed answer lies in the group theory. But yes, you can get an intuitive answer as well with the help of figures, and that has been discussed in details in book by Ashcroft Mermin. So there, basically, if you take say tetragonal and try to take face-centered tetragonal, then that is equivalent to one of the others. So that is not an independent choice. So what is it equivalent to? You go to the book by Ashcroft Mermin, and there is a chapter on lattices. There you try to see why we have only 14 choices of the Brevis lattices. In one of the lectures, I may discuss that also. But before we do that, I leave it to you. At least you do it yourself, so that in that lecture we can have your doubts. I think time is over. So in next class, we will be talking about unit cells in more detail. What is a primitive unit cell? What is non-primitive unit cell? Then we will be talking about criterias which may be taken care while deciding a unit cell. Then we will be talking about the crystal structures. Some of the crystal structures then will be discussed. So that's all for today. I would like to take your questions, if any. Please let me know if there are any doubts, or if everything was okay, then just leave a quick feedback that things were okay. Or if there were any issues, again, yes, Harish, please. Real crystal should have infinite periodicity and should fill the whole universe. It makes me confused. Suppose the real crystal exists, how that crystal should look like, and what is the meaning of fill the whole universe? Yes. Ideally, if you say a real crystal, means it should satisfy the periodicity condition, right? If you take the translational periodicity, so T is equal to N1A plus N2B and blah, 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 right? So that should repeat. And if something is repeating, means a periodic function has a basic defining characteristic that f of x plus a is equal to f of x, means it should keep on repeating. If the periodicity breaks, we can't say that this structure is periodic, isn't it? Because there is a gap. I mean, the periodicity breaks. So ideally, if you even plot a sine function, if I ask you to plot a sine function, and then you say, okay, I plot, say, 10 oscillations, and after that, you leave it there. But then that is not a sine function. That is not fully sine function. Ideally, this should extend all the way from minus infinity to infinity. So you can't plot a sine function on any paper. I mean, it ideally, full sine function will extend all over the space. But yes, for representational purpose, we take care of that thing, and we represent the only few cycles of sine function. Similarly, in real crystal, I mean, there's nothing like an ideal crystal, because ideally a crystal, if it exists in nature, it should repeat infinitely. That doesn't happen. That can't happen, because by some or the other restrictions in the nature, that growth cannot continue to infinity. So that is why there is nothing like an ideal crystal. We may have a single crystal, but that's not ideal crystal. And real crystals are the finite size crystal, and they are having sufficiently long range repetition, but not, of course, up to infinity. Means that's just something which you can call the idealization of reality. In reality, that doesn't happen. That doesn't exist. Is it clear? I mean, so we do this idealization in many cases. There's nothing like ideal thing anywhere in the nature. So I mean, this is a combination of many things. I hope this could satisfy your doubt. If any other question, please. Okay, fine. So I think we are running out of time. So it's already 10:34. Thank you for today's class. Tomorrow we will meet at the same time. I hope I'll share the link well in advance. And I don't know why I have to manually allow you to join the meeting. If someone of you know how can I leave it automatically to you, then that will be nice. I mean, otherwise I have to allow each one of you to join the meeting. But anyway, that's not a problem. That's okay. Fine. Have a good day. Stop sharing. Okay. Stop recording.